Okay, yeah, so so today is virtual. Um, I guess I will go over a couple more examples of some Markov chains that are mentioned in this book, Markov chains and mixing times. And then I will start talking about total variation distance. And so that'll be like the first step toward looking at mixing times. Okay, so here are some more examples. So one is just a variant on this hardcore model that I mentioned last time. So this is the hardcore. Okay, I have to let people in as they join. Okay, so hardcore model with fugacity, which is some constant lambda. So here we again have some graph G, which has vertex set V and edge set E. So this is a graph. And okay, hold on. Uh, the state space is so that this is X is the set of what we called hardcore configurations, but these are also called independent sets of the graph. So remember that this is like, well, I guess if you view it as a hardcore configuration, it's an assignment, it's a labeling of the vertices with zeros and ones so that you don't have any two adjacent ones in the configuration. Um, okay, and so here the stationary distribution of interest is this pi of x. So x is some hardcore configuration, and we want this to be lambda to the sum over v in capital V of x of v. So x of v is either 0 or 1 for each vertex v, and then divided by this z of lambda, where z of lambda is the appropriate normalization factor that makes this into a probability distribution. Um, and so here, the Markov chain that you can use to produce uh, this stationary distribution is you say, well, at each step, choose some vertex v in your set V uniformly at random. And then if there exists an occupied neighbor of V, and by occupied I mean a vertex with a 1 on it, then well, that would force V to be unoccupied in the state that you're currently in, and then you just keep it unoccupied. Uh, yeah, so keep V vacant. And then otherwise, uh, put particle, okay, put a particle on V with some probability, and this probability is if you want the stationary distribution to be this pi that I wrote down, then you want this it turns out you want this probability to be lambda divided by 1 plus lambda. So I think I had earlier chosen lambda to be 1 in the previous way that I introduced this, so that this lambda over 1 plus lambda was a half. Um, but now I mean, you can choose other lambdas instead.
Wait, sorry, can I ask a question really quick?
Yep, yep.
What is, when you wrote the expression for pi of x, maybe you said this already, but what is the x of v?
Okay, so x of v is either 0 or 1. So yeah, I'm thinking of x as a function from the vertex set to the set 0, comma 1, such that any two vertices are assigned not both one, or any two adjacent vertices are not both assigned one. So yeah, x of v is just like either the 0 or 1 assigned to v.
Okay, got it. Thanks.
Yep. Yeah, so here it's like it's gonna, instead of having just like I think when I had lambda is 1, right? So then this was just going to be a 1, but now it can be weighted by this lambda. Okay. And then one other important example is the Ising model. Okay, so here again, G is going to be a graph like before with vertex set V and edge set E, and a spin system is, well, a probability distribution on X, which is going to be -1, 1 to the V. So, okay, well, now it's uh, just every vertex is assigned either a -1 or a 1. And apparently the interpretation of this is using magnets, where you imagine you've put a magnet on each vertex, and each magnet can have one of two possible orientations, and the orientation is either like plus or minus. So in the Ising model, there's this notion of the energy of a configuration sigma. So sigma is in X, meaning it's an assignment of the vertice of -1 or 1 to each vertex. So it's like this configuration of magnets. And its energy is defined to be this H of sigma, which is negative the sum over edges VW of sigma of V, sigma of W. Okay, so let me do an example of this. Okay, so example. Let's say we have this graph here. Uh, okay, so my sigma is going to be some assignment of -1s and 1s to the vertices. So maybe I have like a 1 here, and a -1 here, and a -1 here, and a 1 here. And if I do that, then for every edge, I'm going to take, so if I want to compute the entropy of this sigma, I want to say for every edge, let's just multiply the numbers on the endpoints of that edge. So here, like for this edge, I would get -1. And then for this edge, I'm multiplying -1 times -1 is +1. Here I have -1 times -1 is -1. And then on the diagonal edge, I have a -1 times -1 is -1. So the entropy, or the energy H of sigma, is the negative of this sum, which is going to be -1 plus -1 plus -1 plus 1. And so this is 2. Okay. Okay, so from this, you can define what's called the Gibbs distribution. And so this relies on some parameter beta. And I think in the physics interpretation, beta is supposed to be like the reciprocal of temperature in some sense. So beta is some non-negative real number. Uh, so the Gibbs distribution corresponding to the energy H is the probability distribution. Let's call it mu, and it's on this state space X. Again, X is configurations of negative ones and ones sitting on the vertices. And it's defined by saying that mu of sigma should be, well, it's 1 over some normalization factor that depends on beta, and then e to the negative beta h of sigma. Okay, and I guess I'll just say where this z of uh, yeah, the z of beta is just going to be, well, the sum over all configuration sigma of e to the negative beta h of sigma. Okay, and this z of beta is called the partition function. Oftentimes, partition function is like the term used to say like, well, it's sort of this normalization factor. So it's like if you have a probability distribution where you're sort of summing up a bunch of weights. Here, the weights are these e to the minus beta h of sigmas. Um, then the normalization factor that you have to divide by is like the sum of all of these over all of the states, and that's often called the partition function. Okay. Okay, so I just wanted to mention those, but now we can start talking about mixing times. Okay, so the first thing we want to do, so remember the mixing time is going to be some measure of how long do we have to run the Markov chain before the distribution, which is saying like how likely we are to be at the various states after some amount of time, we want that to be close to the stationary distribution. So like how long do we have to run the Markov chain before we are like very close in some sense? And in order to make this rigorous, we have to have some notion of close for, say, two probability distributions. So we want to have this notion of a distance between probability distributions, and this will be the total variation distance. Okay, so this is so the total variation distance between two probability distributions. Mu and nu on our state space X is going to be, so I'll denote it by mu minus nu, but in this sort of norm symbol sub TV. This is going to be the maximum over all subsets A of the state space of the absolute value of mu of A minus nu of A. Okay. Okay, so this, I guess we'll take this as the definition, right? So it's like you're taking the maximum over all possible events in your probability space, and you're saying you want to know, um, like how, like what's the difference between the probabilities of these events measured with respect to mu or nu, and the maximum that that can be is this distance. But there are other alternative descriptions of the total variation distance, and so we'll talk about a couple of those.
Wait, sorry. So A is just like a subset of the like sample space, right?
Yeah.
Okay.
Yep. And we're maximizing over these. Okay, so I guess I'll just say there are other useful descriptions of uh, total variation distance. So here's a proposition. Let mu and nu be two probability distributions on um, yeah, on X. Then the total variation distance between them can also be computed as 1/2 of the sum over all states X in X of the absolute value of mu of X minus nu of X. So the point here is that instead of having to sum over all subsets of the state space, you can actually just sum over the elements of the state space.
Wait, sorry. In the definition above, it should say A subset X, right? Not A
Oh,
and X.
yeah, sorry. Oh, maybe that was the confusion. My bad. Yes, this should be a subset. Thank you. Yeah, good point. Okay. And but now in the proposition, we are summing over elements. Okay. Yeah. Okay. So I think I won't prove this proposition, but it's in this, if you're interested, it's in this book. So proof is in uh the book Markov Chains and Mixing Times. Uh, and I think it's proposition 4.2. Let me make a remark that there's a similar way to think about this, which is that the total variation distance between mu and nu is actually just the sum over all x in x such that mu of x is greater than or equal to nu of x of just mu of x minus nu of x. And the reason is, well, if you believe this proposition, it's just because you can sort of think like in some sense half the time, like for half of the well, okay, how do I want to say this? If you were to sum this uh over where mu of x is greater than or equal to nu of x, and then you were to do the same sum but over nu of x greater than or equal to mu of x, those would actually be the same. So then if you divide by 2, that's exactly what we're getting here. Okay, and I'll also just mention that you can show that the total variation distance satisfies the triangle inequality. So this is less than or equal to mu minus, let's say, eta. So eta is some third probability distribution. And then here we have eta minus mu. Okay, so it is a distance. Okay, so now I want to talk about what's called coupling, which is this useful strategy that's applied a lot. And so I'll define couplings and I'll talk about how they relate to total variation distance. So a coupling of two probability distributions mu and nu, again on some state space X, is a pair of random variables x comma y, which are defined on X. And the way to say this is you want the marginals of this pair to be like mu and nu. So the way I would write that is, so this is such that the probability that capital X equals some particular state little x should always be the same as just the probability of that state in mu of x. And similarly, we want the probability that y equals some little y should be mu of y, and this should be for all x and y. Okay. So one kind of obvious way that you can get a coupling would be to say, I'm going to choose x to be some random variable whose distribution is mu, so that this first equation holds. And then I'll just let y be an independent random variable whose distribution is nu, and then this will work, right? They're independent, so this is fine. But it's more interesting when you have couplings that are not actually independent. You can construct them so that you don't have them being independent. So let me actually give some examples. Okay, example. So let's have a very simple state space. Let's just say X is the set 0, 1, and we'll let mu and nu be the same distribution. That I mean, yeah, they could just be the same distribution. Uh, and this will be just the distribution that assigns each state probability a half. So mu of 0 is a half, and mu of 1 is a half. And this is all, and nu of 0 is a half, and nu of 1 is a half. Okay, so it's just like a coin flip, basically. Okay, so here are a few couplings of mu and nu. I'll write down a few of them. Coupling 1 is what I was just saying, where you just choose them independently. So here I'll let x and y be independent. So this is called a Bernoulli random variable. So it's basically a coin flip where it takes value 0 with probability half and takes value 1 with probability half. So this is Bernoulli random variable with parameter 1/2. Or be independent random variables should be for with parameter 1/2. Okay, so this is a coupling, but there are others. So here's a different coupling, number 2. Well, we could let x. Okay, so we'll let x be a Bernoulli random variable. Okay, I'll just say Bernoulli with parameter 1/2. And I'll just let y equal x. This is not a script x. This is a capital X, like that. Yeah. Um, so this also works, right? Here, like in coupling number 1, it was sort of like I said, x is determined by some coin flip, and then y is determined by some other coin flip that's independent of the first one. Here, I'm just saying flip one single coin and let x and y both be what you get from that coin flip. So they're the same thing. But again, this is still going to satisfy these defining equations for a coupling because the probability that x is some state is a half, probability that y is some state is still a half, right? And then let me do a third coupling. Well, again, I can let x be Bernoulli with parameter 1/2. And now I'll let y be 1 minus x. So I flip my coin, and if the coin comes up, well, 0, so I have two sides of my coin are 0 and 1. If the coin comes up 0, then I let x be 0 and I let y be 1. And if it comes up 1, then I let x be 1 and y is 0. So they're just opposites. But this will still be, it'll still satisfy this condition. Okay. So how do couplings relate to total variation distance? Well, we have a proposition. Okay, so again, let mu and nu be probability distributions on x. Then the total variation distance between them is going to be the minimum of, so I'm going to take the minimum over all possible couplings x comma y of the probability that x does not equal y. So here xy is a coupling of mu and nu. Uh, yeah, right. And so I've written minimum. You might think maybe I should write infimum because maybe that it's not actually attained, but it turns out it is actually attained. So uh, so I can write minimum. Okay. Um, well, okay, maybe I'll just mention like why does this make sense as like just intuitively why would you expect this to be the case? Well, for one thing, let's imagine mu and nu are the same distribution. In that case, the total variation distance between them should be 0 because they're the same thing. Uh, and in that case, you can take x and y to be equal, right? You can just let x be some random variable distributed according to mu, and then let y equal x. And then the probability that x does not equal y should be 0, which is what we want. Okay, so let me prove this, sort of. Well, okay, I'll give a kind of sketch of a proof. Okay, well, first of all, for any coupling, xy, and any subset A contained in the state space, we have mu of A minus mu of A equals, well, this is going to be the probability that the random variable x lands in A minus the probability that y lands in A, right? So this is just because uh, xy is a coupling, right? So the probability that x is in A should be mu of A, and the probability that y is in A should be nu of A. And this is going to be less than or equal to, well, the probability that x is in A still, but then minus, I'll say the probability that y is in A and x is in A, right? So the probability that y is in A and x is in A is less than the probability that y is in A, because it's more restrictive. So I'm subtracting something that is less, meaning that this is greater than or equal to. Right, so I have this inequality. Okay, and then, well, so now I'm saying this is the probability that x is in A minus the probability that x is in A and y is in A. But that should just be equal to the probability that x is in A and y is not in A. Okay. But if x is in A and y is not in A, then certainly x and y are different. They're not equal. So this must be less than or equal to the probability that x does not equal y. Okay, so what this shows is that, well, the total variation distance between mu and nu must be less than or equal to, okay, here I'll write infimum because we haven't shown that it's a minimum yet, but the infimum over of probability x does not equal y, such that xy is a coupling of mu and mu. Okay, so this is one direction. But now we want to construct, okay, so now we construct a coupling x comma y such that the probability that x does not equal y is actually, let me make this a better x. Is actually equal to the total variation distance. Okay, I think I'll give a sketch of the idea here. I think the book provides more of a rigorous treatment, but hopefully the sketch will be good enough. So let me draw a picture. Okay, so here, no. Okay, so I'm gonna imagine that my state space consists of these little intervals like this. And so here I have, I guess, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 states. And I'm going to represent a probability distribution as like some kind of bar graph or histogram, I guess, where the heights of the bars represent the probability masses. So let's say I have my mu looks something like this. Um, okay, maybe I have this here, then here, and then here. It's maybe not the best drawing, but you get the idea. Um, Something like this. Maybe, okay, whatever. Okay, something like that. Maybe this is 0 here. And okay, so this is my mu. And then I also want my distribution nu. So I'll do nu in uh, green, I guess. So maybe nu looks like this. Maybe it's the same here, but then maybe smaller here. Okay, and in theory, like the area under the pink box in the pink bars is supposed to be 1, and the area in the green bars is supposed to be 1. Probably I drew this poorly, but intuitively that's what's supposed to happen. So this is my nu in green. Okay. And I want to divide this picture into 3 regions, namely the stuff that is, well, I'll break it into stuff that's in this mu region, but not the nu region. So that'll be like this part here. And I'll call this region 1 with a Roman 1. Okay, and then maybe in blue, I'll do region 2, which is going to be the stuff that's under, or stuff that's in the green, but not in the pink. That's this over here. And these should have the same area. Maybe, okay, maybe it's not that off, the orange and the blue. And then, okay, so this will be region 2. And then region 3 is going to be the intersection here. Okay, so now how do we get the coupling? Well, I'm going to choose a point randomly from the region 1 union 3. So basically the stuff that's under the mu, or that's in the mu distribution, I'm choosing something randomly, and I'm going to let capital X be its like X coordinate, which is basically the state that it's representing. Okay, so the point is that this is specifically constructed so that the probability distribution, or yeah, the distribution for capital X is this mu. I'm just saying, like, choose something from the histogram, and that gives you your state. Okay. And then what I'll do is say, if this point is in the region 3, which is the intersection, then I'll just set y to be the same as x. And otherwise, so otherwise meaning if the point was chosen from the 1 region, then I will independently choose another point from, yeah, choose another point from region 2, and let capital Y be its X coordinate. And so this is constructed specifically so that the probability distribution for Y is new. And I'll just note that in this second case, in the case where we had to choose the second point independently somewhere from region 2, so in this latter case, we must have x not equal to y, because in this case, x lies, or yeah, the point choosing, yeah, okay, how should I, so the point that we chose first is somewhere in the orange 1 region, and then the second point is somewhere in this blue 2 region, and notice that their x coordinates have to be different, right? Okay. So this is the sketch of the proof, and again, there's it's written out more rigorously with formulas and stuff and symbols in the book, but maybe this is convincing. Okay. Now, let's see. For any state x, let me just fix this notation. I'm going to let p to the t. So here, this is my capital P, which is my transition matrix for my Markov chain. T is some time, and p to the t of x dot. Uh, this will be the distribution on x given by p to the t uh, with like my initial state being x. Right. So if you think of P as a transition matrix, P to the T is the transition matrix like after time T. And so this makes sense as the notation. It's just um, you think of this as the probability distribution of like it's saying the probability of a state Y is the probability of going from little x to Y in T steps of the Markov chain. Okay, now we're gonna let d of t be the maximum over all states x in x of the total variation distance between p to the t of x dot. So this is some probability distribution and the stationary distribution. And we'll keep denoting the stationary distribution by pi. I guess also, okay, so this is d of t, and I also want to let d bar of t be the maximum over all pairs of states x and y of the total variation distance between p to the t of x comma dot and p to the t of y comma dot. Okay, so these are two quantities that we'll consider. And there's a lemma in the book. I think I won't prove this lemma, but here's what it says. Basically, it says that this d and the d bar are close in some sense. So d of t is less than or equal to d bar of t, and this is less than or equal to 2d of t. So they kind of have the same order of magnitude in some sense. Okay. Um, Now, maybe what I will prove is this proposition, or yeah, so another lemma. So this says that this function. Oh, hold on, I have to plug in my laptop. Give me 1 second. Okay, where was I? Okay, so the lemma is that the function d bar is submultiplicative which means that d bar of s plus t is going to be less than or equal to d bar of s times d bar of t. Okay. So I think I will prove this, and maybe this will be the last thing I'll do for today. Okay, so proof. I'm going to fix some states x and y, and I'll let x sub s comma y sub s be coupling of p to, so here s is some non-negative integer, so it's like a time, some discrete time. So it's a coupling of p to the x of x dot, which is some distribution, and p to the s of y dot. Okay. Um, okay, oh, sorry. So I should say this is a coupling such that the total variation distance between them so p to the s of x dot minus p to the s of y dot equals the probability that x sub s does not equal y sub s. And we said earlier that we can find such a coupling because the total variation distance is the minimum over all couplings such that this probability of them differ, of the probability of them differing. Okay. And I guess I'll denote this by star. So star is the equation saying probability that xs does not equal ys is this total variation distance. Okay. Then if I take p to the s plus t of x comma w, so x and w are some states, well, this is going to be the sum over states z in x of the probability that x s equals z times the probability, or times p to the t of zw. Okay, so why is this? Well, p to the s plus t is the probability of going from x to w. Sorry, p to the s plus t of x comma w. That's the probability of going from x to w in s plus t steps. So that should be the probability of going from x to somewhere in s steps, and then going from that somewhere to w in t steps. But the point is, well, okay, I could have written this probability that xs equals z. I could have written that as p to the t of x comma z, but I can write it this way because this is a coupling, right? So because xs right? Because this is a coupling for these two distributions, in particular, the probability that xs equals z is p to the s of x comma z. Okay. But then I can say, well, this is just an expected value sum, right? Like this sum is just like the definition of an expected value. So this is the expected value of p to the t of xs w. Okay. Okay, thus for A, any subset of the state space X, we have that P to the S plus T of X comma A. So this is the probability of going from X to somewhere in A in S plus T steps. This is so okay, this minus P to the S plus T of Y comma A. This is going to equal the expected value of P to the T of X S comma A. So this, I'm getting this by just taking this equation here and I'm summing over some set uh, A. So I want to take expected value of P to the T of XSA minus P to the T of YSA. Okay, maybe I should unpack what I'm doing here. So if I take this, so this term is the expected value of P to the T of XS comma A. So it's this expected value. And that's just by taking this identity and summing over W in A. And then I have a similar thing saying that this is the expected value of P to the T of YSA. Okay. So like this is expected value of this. And that's for the same reason, except just with little x replaced by little y. So really, I should have written this, I guess, as expected value of p to the t of xsa minus expected value of p to the t of ysa, but you can use linearity of expectation and say that actually it's the same as the expectation of the difference. So that's what I've done. Okay, now this is less than or equal to the expected value of d bar of t, and then the times the indicator function of the event xs not equal to ys. Okay, why is that? Well, if xs and ys are equal, then that will cancel in this expression. So I only care about where they're not equal. And then this d bar is, we go back to the definition of d bar, it's going to be the maximum of the total variation distance between these. So here I have like these particular uh like xs and ys, and wait, oh right, yeah, okay. Yeah, I think okay, you can show that it will be less than or equal to this. maybe there's a step of thinking about it, but I think it's not hard. It essentially should follow just from the definition of d bar. Okay, but then this is the probability that xs does not equal ys times d bar of t. I'm just sort of factoring out the d bar of t because that's not random. That's just a number depending on t. And then I have the expected value of this indicator function is just the probability that xs does not equal ys. Okay, and then finally, if I use this equation star, so star was saying that probability of xs not equal ys is equal to the total variation distance between p to the s of x dot and p to the s of y dot. We get that we know that the probability that xs does not equal ys is less than or equal to d bar of s. Okay, so this is just using this here, star, and then the definition of d bar. Okay, and so what does that mean? Well, so that means that, so p to the s plus t of xa minus p to the s plus t of ya is less than or equal to no, d bar of s, d bar of t, and then you can take a maximum over these sets A, and that proves the submultiplicativity. Yeah. Okay, any questions about this? Okay, so I think I'll stop a few minutes early today. And then next time I'll probably just it'll be sort of a relaxed class where I go over I guess a talk that I'm going to be giving, and you can come if you want, but yeah, don't feel obligated. It's just sort of a bonus class. Okay, so I think that's all for today.
Thank you.